You are listening to Think Theory Radio. Radio. Hello and welcome to Think Theory Radio, the show that brings you topics outside the mainstream realm of thought and ideas to make you think. And I'm Damian Perdue, your host and your guide on this metaphysical ride of audio delights. And of course, I'm joined by the one and only Physics C.
Yo. My physics teachers from high school would correct you on that one.
Well, you know radio physics.
I suppose
you know how
so.
to work the pots up and down.
Could not explain how it gets from the studio to the transmitter and from the transmitter
frequencies
to our
and
ears,
vibrations.
Yeah. To hertzes and all that.
Yeah.
It hurts just thinking about it.
All right. Well, since you're no expert, I'm going to have to bring on the expert. And that is theoretical astrophysicist and cosmologist Dan Hooper from Fermilab and the University of Chicago. What's going on, Dan?
Hey, Damian. How are things?
Good. How you been?
Yeah, things are right. Things are a little duller than usual in pandemic times, but we're all coping.
Yeah, how's that been going? It's been a while. I think had you on back last, right when the pandemic started, I think. It was like March or
that could have been it.
It was right around then. Are you still doing everything remotely?
Yeah, just about. I taught a class in person last fall, but other than that, I've been doing all my work from my home office and using a lot of Skype and a lot of Zoom.
Yeah, I can imagine. And, I actually I follow Fermilab on Instagram, and I just saw the other day that they're starting up virtual tours. And that seemed like a pretty cool idea. I didn't really get too far into it. Just showed a bunch of different pictures of the different labs, and you can join in and everything like that. So we're figuring out ways to get by.
Yeah, Fermilab is a pretty amazing, site. Not just because of all the science that's been done there over the years, but it's just a gorgeous main building and campus, and you can, go up onto the 15th floor of that building and overlook the old Tevatron particle accelerator ring. It's just a fantastic thing to check out if you ever get a chance after the pandemic's over.
Yeah, I definitely want to. And I know, we talked about doing it right before and it just couldn't set it up. And then, the whole world collapsed. And
as soon as we're all vaccinated.
Right, exactly. And then I will come take a tour because I've definitely been wanting to check the place out. It just seems not only just the experiments there and everything that goes on, but the history there is pretty remarkable as well.
Yeah. A lot of great things have been done there. A lot of brilliant people have worked there over the years.
Yeah, and I'm also interested, too, in the art gallery. Being an artist myself, I noticed they have an art gallery there, and some of the artists that have done residencies there have been pretty incredible, too. So that definitely...
Yeah, I don't dig every exhibit we have rotating through there, but there have been some great ones that I really have gotten a lot out of over the years.
Yeah, I can't remember the name, but I think she was one of the original artists for Fermilab, and I saw some of her, I don't know if they were paintings or drawings, but she did these really cool kind of mystical, she had these kind of like witches with a cauldron, but then there were like particles jumping out of it. And
you're talking about, what's her name? She was our artist in residence for a really long time.
Yeah. And I think she passed away recently, and that's why I read about it.
She has passed away. I'm trying to Google her name right now so we can do her justice.
I think I want to say
come back to you about that.
It's all good. Yeah, I think like Marguerite or something has but I could be totally wrong. But anyway, I digress. So we've had you on the show numerous times, and we've talked about dark matter, dark energy. We've talked about black holes. We even talked about how a civilization could harness a star's power to travel, interstellar travel. So I figured we've not that we've covered all of the macro, but we'll go from the macro to the micro and get into one of the quantum physics aspects that I find very, very fascinating. Not that it isn't all fascinating, but quantum entanglement.
For sure.
And so let me try my layman explanation and see if it fits right. So then you can give the real explanation of what it is. So quantum entanglement is when two particles interact, and after that interaction, after they separate, no matter the distance of space or time, they will have an action opposite of the other particle. Am I explaining that
or
right?
at least related.
Okay,
they don't necessarily
related,
have to be
okay.
opposite. In most of the simple examples, they're opposite. But the state of one particle will depend on the state of the other, and vice versa.
Okay.
And it can be a complicated. It doesn't have to be just two particles too. It can be any number of things. It can be entangled. It's this really weird facet of quantum mechanics that I think before people invented quantum mechanics, no one would have just guessed the universe would work this way. So let's walk through a simple example.
Okay.
So this all started when Einstein was looking at the theory of quantum physics, and he says, like, oh, this just doesn't smell right to me. It just there are things I think have to be true about the universe, and they're not in this theory. So I'm going to try to think up reasons for why this theory has to be fatally flawed. And he wrote this paper proposing what he thought was a problem with his collaborators, Podolsky and Rosen. So it became the EPR paper for their names, Einstein, Podolsky, Rosen. Mm-hmm. And in it, he proposed, well, what he proposed a little bit different from this, but I have a simpler version that I think will get the message across. Imagine you have an atom that decays. And when that atom decays, it disappears. And in its wake, it leaves behind two photons. They're going in opposite directions, kind of like back to back. Okay?
Okay.
And if one is spinning in one direction, then the other one has to be spinning in the opposite direction in order to balance their angular momentum. So there was no angular momentum before they were created, so their spins have to be equal and opposite to each other. But quantum mechanics says that one of these guys isn't spinning one way or the other. It's spinning both ways at once. It's in a superposition of both of those states at once. So, if I told you a coin is facing heads up or tails up, you'd know what that means. But in quantum physics, a quantum coin is facing both heads and tails up at the same time until you look at it, and then it collapses into one or the other of those two states. So in the same way, this photon is spinning left, and it's spinning right. And the other one, if the first one's spinning left, the second one's spinning right. If the first one's spinning right, the second one's spinning left. Now these two particles get far, far apart from each other, and I bother to measure one of them. And I find it spinning one way or the other, and it seems like I instantly now know how the other one's spinning. But like, how did I learn about something a long way away from me instantly? That seems to violate all sorts of problems. It seems to violate the speed of light, or that's that cosmic speed limit we all think is fundamental in physics. It seems like a real problem, or at least it did in 1935 or whatever.
Now, that's what I was going to ask you too. Well, I have a couple questions. So in the 1930s, they came up with the concept of it, or the theory of it. But it's just been recently that they've proven it, right?
Yeah, so a lot has changed in the, most of a century since Einstein's paper. For one thing, it doesn't really seem to be a problem to most theoretical physicists anymore. We all agree it's weird, but it's okay. I mean, things can be quantum entangled, and it doesn't screw up with any logical foundations of our universe. It's just weird. It just means things that are far apart from each other can be in quantum states that depend on one another in kind of complicated ways. Okay. Yeah. And the other thing that's changed a lot in that time is we've developed technology to manipulate quantum systems in really sophisticated ways. We're starting to build things like quantum computers. We can definitely put quantum objects, quantum particles in superpositions that are entangled with others. We can basically do all the sorts of things Einstein was daydreaming about in the 1930s. We can do that stuff in the laboratory now.
Okay. Now, what's the difference? Because I know a lot of the experiments now, and it seems like within the last couple of years, there's been just this kind of rapid acceleration, no pun intended, but of quantum experiments with quantum entanglement, but also quantum teleportation. Now, are those two the same, or what's the difference between quantum entanglement and quantum teleportation?
Well, quantum teleportation relies on quantum entanglement. I warn people not to take the word teleportation too seriously here. It's not that, it's still the case that no object can move through space faster than the speed of light. That is still a law of physics. Quantum entanglement doesn't allow you to break that law. It seems to at face value, but it doesn't when you look deep down at it. So nothing moves through space faster than light. But still, there's this phenomena we call quantum entanglement, called quantum teleportation that's closely related to quantum entanglement. All these things are kind of like close cousins to each other.
Okay. Now, that's the other thing, too, I was going to ask, because I see there's a lot of liberties taken when, quantum physics enters kind of the pop world or popular culture, movies, mainstream stuff. Sure. And I've seen kind of time and time again the use of quantum entanglement as saying that it's faster than the speed of light, which it's not. But what's the difference between how is quantum entanglement not faster than the speed of light, or what's the difference, I guess?
So the real limitation is you can't build any kind of machine using quantum mechanics or anything else that can allow me to take a message that I have in my hand at this place and time and get it somewhere farther away from me than light could have gotten in that same amount of time. Mm-hmm. That's the real rule that's built into Einstein's theory of relativity that we take very seriously in modern physics. Yeah. You can do things like collapsed wave functions that are extended over time and stuff, but you have to do things to make that wave function be extended across space first. And when you're actually done doing the whole experiment, nothing traveled faster than light. So there's if there's some place a light year away from now, there's nothing I can do now that can influence that place in less than a year. No matter what I do, no matter how I build my quantum machine, or no matter what I entangle or what I quantum teleport, nothing I can do here can affect that until a full year has passed, allowing light to get there at the speed of light.
Okay. Now, let's get a little bit philosophical, but also I'm curious as to the relationship between quantum entanglement, the universe itself, and ourselves, knowing that, the carbon and iron and gold and everything that's within our bodies come from these, star mergers and galaxies colliding and all the way back down to the Big Bang itself. Now, if particles that interact with each other are connected, no matter the distance, space, or time, does that mean that the particles within our bodies are reacting to particles from the Big Bang? Does that make sense, or is that...
Well, yeah, so first of all, I mean, a lot of the particles in our universe today, including a lot of the particles in our body, were created in the Big Bang. In the first few minutes and seconds, all of the nuclei and all the hydrogen and helium and most of the lithium and beryllium in our universe, all that was made through fusion in the very early universe, when the whole universe was basically one giant fusion reactor. 100 billion degrees throughout the entire universe. In those first few minutes, those neutrons and protons bound up together to make the building blocks of atoms that we have in our universe today. Now, all the heavier stuff, all the carbon, oxygen, iron, uranium, gold, silver, whatever, all that stuff was made in stars. But most of the helium, lithium, beryllium, and hydrogen, all that stuff was there from the very beginning. So, we are, pick up almost any piece of matter in the universe today, and it has stuff from the very beginning of our universe, built into it. And then as time goes on, of course, many, many different events transpired and changed the composition of our universe, including fusion going on in the cores of stars, including the explosions of stars that we call supernovae that distribute those different nuclear elements across space, across galaxies. And then you mentioned things like, galaxies forming and galaxies colliding and forming bigger and bigger structures. All of this evolved, planet formation, all that sort of stuff. And yeah, it left the universe in a pretty interesting and deeply interconnected state that we find it in today.
Okay. Now, as far as the quantum entanglement, the theory, and when it first came out in the 30s, what was the reception to it, especially to classical physicists or people like Albert Einstein? I know he called it spooky action at a distance. Was it something that was kind of like heretical in a way, or did they view it as pseudoscience, or was it like accepted early on?
Well, so the first ideas of quantum mechanics like kind of started in 30 years earlier than that, in 1905, with Einstein's paper on the idea that light might be made up of particles, what we now call photons. And that was what got him the Nobel Prize eventually, for example. Little side note is he never got a Nobel Prize for relativity, probably the greatest scientific theory of all time. He never got a Nobel Prize for that for a bunch of complicated reasons, but he did get one for the theory of photons as light, so that at least he got that credit where it was due. And then, some years after that, so basically Einstein 1905 said light is a wave, but it also is made up of particles. And then, 10 years later, people like Niels Bohr were arguing like electrons are particles, sure, but they also act like waves. And by the 1920s, all this was kind of culminating in what we now call quantum mechanics, where everything is a particle and a wave simultaneously. Everything is in a superposition of states. That means that there isn't something at one place at one time. Things aren't moving with one velocity. The events that happen don't occur at one particular point in time. Instead, everything that exists in the universe is in a superposition of different times, places, and motion, all at once in a complicated, array of states all interacting with each other at the same time. So by the 1930s, most physicists who studied this sort of thing accepted that the theory worked. It made too many very accurate and correct predictions for it to be all wrong. But I think a lot of people were looking at this theory going, oh, it's so weird. We must be thinking about this wrong. Like, maybe this math works, but we must be approaching it wrong because it's just so bizarre. I know Erwin Schrödinger, one of the main pioneers of quantum physics, felt this way. Einstein certainly felt this way. Later on, people like Eugene Wigner and stuff would have deep misgivings about it. And it's really counterintuitive. It's really strange. But to this day, we have never done any experiment that contradicted any prediction of quantum mechanics. It's just a theory that keeps holding up to scrutiny no matter what test we do. I think it's just the case that the quantum mechanics it works, and to whatever extent we trust the scientific method to arrive at truths about the universe, we should view quantum mechanics as a truth about the universe.
All right. And you said it there, strange. I think that's one of the reasons I like it, is it's so strange and esoteric. It's just
Me too.
And you mentioned the experiments, so we got to take a quick break. When we come back, I want to talk to you a little bit about the experiments they do to prove quantum entanglement and quantum mechanics, and also the facilities like CERN and Fermilab. And we'll be back with more Think Theory Radio right after this. Welcome back to Think Theory Radio. This is Damien, and today I'm joined by astrophysicist Dan Hooper, and we're getting into a fun discussion about quantum entanglement and quantum mechanics. And before, in the last segment at the end, you had mentioned the experiments and how they've just constantly proven that quantum mechanics work. Now, what kind of experiments have been done to prove these theories correct?
I mean, there's so many different ones. It's hard to even know where to start.
But what's your favorite ones?
My favorite ones are the big ones.
Okay.
So you take a machine like the Large Hadron Collider. Okay, so this is the world's most powerful particle accelerator.
And that's at CERN for people that don't know.
It's CERN, yeah. And it's a big laboratory, kind of the European version of Fermilab. And it's, in Geneva, Switzerland, and it actually spills over into past the border of France. So they've got this enormous underground tunnel I want to say it's 27 kilometers in circumference. I don't have the number memorized right now. And it's a couple hundred meters underground. And around that circle, that underground tunnel, they use powerful magnets to accelerate protons to just about the speed of light. I think it's 99.9999997% of the speed of light. So very close to the speed of light. And they get one beam of particles going one direction around that circle, and then a second beam going equally fast in the opposite direction. And then at designated points, they cross the two beams and collide them head on to each other. And at those points, you get protons, individual protons colliding with other protons, getting so much energy at one point at one time, one place at one time, that we can create entirely new kinds of matter, new kinds of, stuff that just doesn't exist in our day-to-day experience. We can produce things like Higgs bosons and top quarks and W bosons and Z bosons, and the list goes on and on. These exotic forms of matter are usually unstable and they disappear pretty quickly, but in that moment that they exist, we can measure their properties, learn how they behave. In other words, we can learn what forms energy can take in our universe, how they behave, and fit that information into our most sophisticated theories of what we call quantum field theory, or really the modern version of quantum mechanics.
Mm-hmm. Now, if you can't technically see these particles, how do they capture that? How do they figure out how these interactions?
Yeah, so these collisions take place in these machines. We call them particle detectors, but they're like gymnasium-sized, sophisticated collections of electronics. Mm-hmm. They have different layers, each of which are designed to measure different things. So, for example, maybe a high-energy photon shoots out of the collision in some direction, and there's an electromagnetic calorimeter, which is a type of detector which tells that photon hit in a given direction with a certain amount of energy. There are other kinds of detectors that can track the path of a muon, a different kind of particle, and there are others that detect other kinds of particles. And all this stuff is recorded, in a blink of an eye. There's something like 600 million collisions happening every second at LHC when it's on. So we're talking about, incredibly sophisticated computers that can record all this information and then process it and kind of look for the needles in a haystack of the most interesting events where the stuff we really want to learn is hidden.
Now, I've seen kind of, I don't know if you'd call them pictures of these particle collisions. They're kind of like, they remind me of like lithograph or kind of etches or like wood etching. Do you know what I'm talking about? That shows the particle collisions?
Yeah, I've seen a bunch of different kinds of depictions of these things. Usually the way it's done is you're kind of like looking down the beam line.
Okay.
And then you see all the stuff kind of come out in different directions. And some of the lines are straight. Some of them are curved. The straight ones are the electrically neutral particles. The curved ones are moving because they're on a magnetic field, kind of going in little spirals. Others look like little sprays of explosions. All that stuff goes into the computer, and they take all that information and reconstruct how the event played out.
Okay. Now, I was reading too that Fermilab, I think they're going to start a new project with a photon beam. I think it is. Do you know what I'm talking about?
Well, I don't know about a photon beam. There are a number of really exciting things going on at Fermilab right now, and there are always ideas on the table that I might not necessarily be privy to. So you might be right. So one of the things I'm really excited about, which I guess we're supposed to hear, the results from pretty soon, is something called the G-2 experiment. So this is a really precise measurement of something called the muon's magnetic moment. So muon is this particle. It's kind of like an electron, but it's heavier, and it only lives a millionth of a second before it decays. So it's like an unstable, heavy electron. And its magnetic moment is just like a number that describes how it interacts when you put it in a magnetic field, what it does when you put it in a magnetic field. And, this is a number that we can predict from our theory, from quantum theory. And about, 15 years ago, a different experiment in New York made a measurement of this, and they got a different number than the prediction of the theory. If that's true, it's super interesting. I mean, maybe the theory is broken, which would be incredible, but more likely the theory's right, and there's just some other particles that we don't know about that are interfering with the muon in such a way to make it behave a little bit differently. And I'm not talking about like a big difference. I'm talking about a very, very minuscule change, but we're so good at making these measurements that we can look for really minuscule changes. And if a Fermilab experiment confirms that the measurement is off of the prediction, it will be hot on the trail of discovering new kinds of particles, which mean new kinds of energy that exist in our universe, and trying to figure out how they fit into the big picture of things.
Now, would that relate to dark matter or dark energy in any way?
Well, it could. So, for example, one idea for how you could change the magnetic moment of the muon in a way like we're talking about would be to introduce a new kind of force-carrying particle. Let me unpack that a bit.
Okay.
So the forces we have in nature, like the electromagnetic force or the strong or weak nuclear force, presumably gravity too, but we don't really know how that works. But the forces are all manifest in nature because of some particle that communicates the effect of that force across space. So if I have two charged particles, they repel or attract each other through electromagnetism, but the way they do that is because photons are being passed back and forth through space. And so in other words, the photon is the thing that makes the electromagnetic force work. If photons didn't exist, there wouldn't be any electromagnetic force and vice versa. So it's possible there are other particles like this that we don't know about yet that would create or manifest new forces that we don't know about yet. These forces might be really weak. That would explain why we haven't seen them yet. Or it might be that they only interact with particles that we have a hard time measuring. That sort of thing is possible. And if there's a light force carrier like this, we call this thing a Z prime boson. That's the nomenclature. Maybe that thing explains how the dark matter interacts with stuff, which would make it a weak force and the sort of force you'd want dark matter to feel. It could explain how dark matter was created in the early universe. It could explain why we haven't been able to see it in our experiments so far. So yeah, the G-2 experiment could, potentially put us down a road towards figuring out the problem of dark matter, if we're lucky.
Okay. Now, here's a very sci-fi theoretical question for you.
My favorite.
Could dark matter or dark energy be the proof, or not proof, but the kind of the existence of a parallel universe? Could it be that this kind of parallel universe is bumping against our own and we don't know what it is, and their matter, their energy is the dark matter and dark energy?
Well, I'll tell you about a theory that I worked on years ago that is kind of close to that.
Okay.
Okay, so it's a theory where there are extra dimensions of space.
Yes.
So what I mean by that is, we know of 3 dimensions of space. We have, left, right, up, down, forward, backward, or something like this. Mm-hmm. And in other words, what I mean is to specify a location in space, I need 3 numbers. Okay, that will do it. But maybe there are more. For example, maybe there's a 4th spatial dimension, and it's wrapped up in a little circle. So, imagine our universe was such that if you went far enough in one direction, you'd come out the other side. I like to compare this to the old video game Asteroids, where you fly off the screen and there you are on the other side of the screen.
Or Pac-Man, when you go through.
Pac-Man does the same thing. Yep, definitely. So maybe a dimension of space is like that. And if that dimension of space is really small, then only really small things can perceive it or travel through it. And it turns out that the size of an object, a particle, its wavelength, if you will, is inversely proportional to its energy. So the more energy something has, the smaller it gets, and the more easily it would be able to move through that dimension of space. And maybe that energy is high, so none of the particles we experience normally can see the extra dimension. It's just invisible to them. All right, so stick with me 1 second farther.
Okay.
Imagine there's a particle right now, like a photon, and it's zipping around that extra dimension. What would that look like to us? It wouldn't seem like it's moving because we don't see that dimension. To us, it's just stationary. It would be like something with a lot of energy that's not moving. And because of Einstein's equation equals mc squared, all that is something that has a lot of mass, a big heavy particle that's not moving. So in other words, the papers I used to write about this sort of thing, and a lot of people did too, were proposing that maybe the dark matter are ordinary particles that are moving through other dimensions of space.
All right.
I wouldn't put a lot of money on this particular theory, but it's a possibility.
So we can use quantum entanglement to teleport ourselves into this parallel dimension, right?
Yeah, I would. That's probably not in the cards, but yeah. But you could build particle accelerators that would give particles enough energy to move through that extra dimension of space, if it existed.
Okay, now explain extra dimension. So one of the things, when you watch sci-fi shows or, any kind of like mystical kind of thing, and it's like they're from another dimension, but it wouldn't be really like a living creature from another dimension, right? Another dimension is more of a direction in space and time than it is a parallel universe. Is that correct?
Yeah, so this isn't a parallel universe. This is literally an extra dimension of space in the same sense that we have 3 dimensions of space. Now, but you can easily imagine theories with extra universes, parallel universes, if you will. Maybe those are, totally spatially disconnected from our own. Maybe they're connected through one of these extra dimensions. So, for example, there could be a 3-dimensional space that we live and another 3-dimensional space. We would call these spaces branes, B-R-A-N-E-S, and they could be connected by another dimension that for some reason we can't, the particles we observe don't propagate through. And we call that space the bulk of the universe. And you could concoct concoct theories like that. And in that case, maybe you could somehow build a particle accelerator that could send messages or things back and forth from one brane to the other.
Yeah, and I've seen that there are physicists working on experiments like that, where they're trying to use these particle accelerators or different kind of, for lack of a better term, atom smashing kind of machines to figure out if there's a mirror universe and all these strange theories. But I love it. It's one of the most fascinating aspects of physics to me is quantum physics, and just this kind of mysterious realm that exists within us, and we exist kind of within it, and it just fascinates.
I never would have become a physicist if it weren't for quantum physics. I mean, I didn't think physics was interesting in high school. I mean, doing inclined planes and simple circuits and stuff. But, I'm in college, I'm kind of wandering, I'm not enthusiastic about anything I'm studying, and I wound up taking a 1-quarter class in modern physics. And in that quarter, I learned just some rudimentary things about quantum mechanics. I learned some rudimentary things about relativity. And these were the 2 most exciting things I'd ever heard about in my life. I didn't really understand them, but I could tell they were super counterintuitive. They were super bizarre. And I was instantly hooked. I changed my major, very quickly and never even for a second looked back. It also had the added benefit of turning me into a good student. I was never a good student before that.
Yeah.
But overnight, I became, a very, very hardworking student just because it was easy to work hard when you were as excited about something as I was.
Yeah, definitely. I mean, in the layman's sense of myself, it's similar because when I was in high school, studying physics or math, I was not really that interested. But then years later, when I started to learn about quantum physics, it got me so much more interested. And when I read books on it, it's just it's a lot easier for me to read than a lot of other subjects, just because of the fascinating nature of it. But what made you, so you quantum physics or quantum mechanics or whatever kind of brought you into...
Yeah, same thing.
Yeah. Now, why did you not become a quantum physicist, but instead go the astrophysicist route?
Well,
And how are the
There are
two
a lot of-
related? So
There are a lot of astrophysicists that think I'm a particle physicist.
Okay.
And there are a lot of particle physicists who think I'm an astrophysicist. I'm kind of in that gray area. No one wants to call me their own.
Okay.
But it's a little lonely, but it's okay. In all seriousness, no. I mean, like, I went to grad school to study physics, to study particle physics, and my advisor kept pulling me towards some interesting problems in astrophysics. And I kept finding that if you knew a little bit about particle physics, which is really the modern version of quantum physics, and you knew a little bit about astrophysics, there was all this cool stuff you could do that other people weren't doing. Like think about dark matter, because dark matter is an astrophysics problem, but it has everything to do with particle physics.
Right.
And many, many other examples like that. So I found myself working kind of at the interface. I'd like to think of myself as a particle cosmologist.
Okay. Now, when did the two? Because I know at a point in time, I don't know, maybe 100 or more years ago, particle physics and classical and astrophysics, or I don't even know, was astrophysics a thing back then? They were kind of separate, maybe. Right? It was a point in time where they started to merge, but before that, they seemed to be kind of separate fields.
So, I mean, more and more, all of science, probably all of academia, is really, divided into tiny little subfields. You can find people who are just like world-class experts in like planet finding, okay? Who know almost nothing about some other kind of physics. And you can find people who are amazing thinkers in the field of string theory who couldn't describe, how to make a basic engine work or something. We really do like hyper specialize. And there are examples of people who know a lot about a lot of things, but a lot of us really are very narrowly focused in our research. And I'm guilty of that as much as anybody. I know a lot about the things I'm interested in and have worked on, and there are a lot of things I don't know much about at all. Like one thing I'm kind of ashamed of is I don't know much about condensed matter physics at all, which is a huge branch of physics. It has to do with how solid materials behave, and it has a lot of quantum stuff involved in them. I don't know much about it, even though it's a huge part of our field. I've never taken a course on it. I've never worked on it. I occasionally see a seminar or something, but frankly, I don't really follow them that well because I don't know enough. And I think I'm not alone. I think a lot of my colleagues, really focus on the thing they're focused on, whether that be in astrophysics or in physics or really any other piece of science or academia.
Yeah, and you reminded me of a documentary that I watched on Netflix. I'm trying to find the name, and I cannot find it. But it was, maybe you've seen it, but it's basically they had 7 different scientists, and they did kind of a telephone game thing where they started off with I believe it was a microbiologist, and then it went to a particle physicist, then to a marine biologist, another physicist, and so on and so forth. And the way they did it was really ingenious because they started off with the first scientist, and she explained what she was doing and, what her field was. And then they literally sent her overseas to visit the particle physicist who they had never met before. And then he started teaching her about particle physics, and then they started to like have this kind of epiphany moment when they realized the similarities between all these different aspects of science. And I really wish I could remember the name right now. I tried to look it up, I couldn't find it, but it's really good. It's on Netflix, and it was interesting to see how all these different scientists in unrelated fields started to notice the similarities and the coincidences between each one and how much they were more interrelated than they realized.
Yeah, I think deep down, a lot of fields have a lot in common with other areas. They might use different language or even different concepts to talk about things, which makes it hard to translate across different communities. But okay, here's an example that I think is really incredible. Is in the early 20th century, philosophers and mathematicians started to work out the different branches of math were really just different ways of describing the same thing. People like Bertrand Russell and Alfred North Whitehead and David Hilbert and others worked to essentially map one branch of mathematics onto another, showing things like, arithmetic and logic and geometry were all really just the same thing written in a totally different language. And I suspect if you look deeply enough at just about anything, you will find those same logical structures and, just presented in a different language, a different way of constructing the ideas, but the same ideas deep down if you could see them clearly enough.
Mm-hmm. All right. Well, now, speaking of interrelated things, now we have to take a quick break, but when we come back, I want to switch gears, but also kind of stay on topic and talk a little bit about music and your role in music and how that relates to physics. That when we come back with more Think Theory Radio. Welcome back to Think Theory Radio. This is Damien, and I'm joined by astrophysicist, particle physicist, astroparticle physicist, Dan Hooper. It's hanging with Mr. Hooper here on Think Theory Radio. There's a title for your new podcast.
Noted.
Speaking of podcasts, you have one, Why This Universe?
That's right. So I started this less than a year ago with now grad students at NYU, Shalma Wegsman. We co-host it. She does all the technical parts too, which is awesome. She's really good at it. And we do these, 25, 30-minute explainers on different stuff we think is cool in astronomy and physics and cosmology and sometimes other fields. We just recorded one on symmetry and something called Noether's theorem. A while before that, we did a couple on black holes, done a lot on quantum mechanics, a lot on cosmology, a lot on the Big Bang. And, we're open-minded to other things. If people want to tweet at me or something, give me a suggestion for a subject, we'll probably take you up on it.
Yeah, I've been checking them out. They're really good. And I like that they're kind of short. They're usually about 20 minutes. It's a nice little kind of concise thing you can listen to when you're taking a little car trip or something,
there are a lot of great physics podcasts that are kind of long form.
Mm-hmm.
So we deliberately set out to do something different. We thought there might be a hole in the market, if you will, for people who might want a kind of punchy, short, but, explanatory version of those podcasts.
Yeah, I think it's a good idea because especially, nowadays people are so much in a rush and don't always have the time to listen to, an hour or 2 hours worth of stuff, but want a little bit of knowledge, wherever they go. I figured out the artist that we were talking about earlier. Is it Martel Langsdorff? Does that sound right?
I think it's Angela Gonzalez.
Oh, you are right. It is Angela Gonzalez. Now that you said that, yes, you're totally correct.
I also Googled it and I immediately recognized her name when I saw it. But yeah, she's awesome. I don't know for how long she worked at Fermilab, but it was, decades, I think. And she designed like tons of our conference posters and things, and there was all sorts of her art everywhere. I just love everything she's ever done. It's just fantastic. Most of it's in black and white, and it's just this kind of surrealist, geometry-driven wackiness. I love it. I love it.
Yeah, that's right up my alley. So I was, unfortunately, if she's not alive. If she was still alive, I'd have her on the show. But
yeah, she would be awesome, I'm sure.
Yeah, definitely great work. But speaking of art, let's switch over to music. And, one thing is you're an astrophysicist, a cosmologist, and, but you're also a musician. And you play in a band called The Congregation.
Yeah, I've been in that band for, I believe it's 11 years now. It's been a great ride. We're a Chicago soul band. There's 8 of us. Gina Bloom is our front person. She's an awesome and powerful soul singer. She's amazing.
She's a great voice.
And then we got 3 horns, drums, bass, myself on guitar, keyboards, organs, whatever. and kind of in the Stax sort of tradition of soul music, I think. But mostly we write our own music, and we've got 3 records out there, and we're working on a 4th recording now. And we've done pretty well for ourselves over that 11 years. We've had the honor of opening for Mavis Staples on one occasion. We opened for Wilco once. We opened for Garbage and the Flaming Lips on another show, and
Nice.
we've opened for Buddy Guy. So we've it's been a real roller coaster ride with that band.
So not only you're a scientist, but you're a rock star. Come on, man. You can't have it all.
I'm not complaining.
Actually, it's funny because you're the 3rd scientist I've had on the show that actually also has artistic passion as well. I had a neuroscientist on, and she's an abstract painter, and I had a systems analyst who's also a musician. And I find it fascinating, the correlation between science and art. I think there's definitely this kind of a yin and yang thing with art and science, and it just kind of in an abstract thought. This is Think Theory Radio. I was thinking about the relation, especially because when I saw you playing the guitar, and I was like, okay, perfect. He's a guitar player, right? And I thought about Nikola Tesla's. He has a quote: "If you want to understand the secrets of the universe, think in terms of energy, frequency, and vibration." And I think of string theory, right? So I'm putting together in my mind this kind of weird formation of guitar strings and string theory and sounds, right? Like sound waves and, wave fields. But I don't know how to put it all together. Have you ever thought of anything in that kind of abstract terms in relation to your music playing?
Well, the thing I've noticed the same thing you've noticed. A lot of my colleagues, a weirdly large fraction of my colleagues, are accomplished musicians or in other things too, but a lot of musicians. And there's everyone knows hobbyist musicians or whatever, but there's a surprising number of really good musicians among the physicists I know. And like, part of me thinks the explanation's got to be something about when a brain is configured in such a way to make them good at doing math and physics, it's also good at doing music or correlated in some way. But another part of me just thinks like we tend to have pretty obsessive personalities. Like when I decided I really liked physics, I spent all my waking hours reading about physics and working physics problems and thinking about physics. And when I was really excited about guitar playing, I played guitar for 5 or 6 hours a day. And those, that's maybe doesn't require the brains to be all that alike. It just means I have the sort of personality that when I get into something, that's kind of what I do. It's just an obsessive characteristic that might have something to do with it, or maybe it's some combination of both things. I really don't know. I don't have a good conclusive answer to this question.
Maybe you're tapping into the secrets of the universe when you play the guitar, man.
Yeah, maybe.
And actually,
I'll write that up as a new theory.
There you go.
And see where it goes.
It could be a new book, the physics of music. If you need me to write the foreword, it's all good. I'm there for you.
All right. Good to know. Good to know.
And but speaking of music and sound and how it relates to, let's say, astrophysics, was there sound at the beginning of the universe?
Sure. So all sound are pressure waves, right? So when the universe was originally filled with, let's back up. So today, it's a pretty hard place for a sound wave to do much of anything. Most of space is empty. You can't have a pressure wave move through empty space. So basically, it's a quiet universe today. The only places a sound can really propagate are where there's a lot of gas and stuff, or liquid or whatever, like on a planet's surface, for example. And sometimes in gas clouds and things. But basically, most of the universe is quiet. In the earlier universe, it was much denser. The whole universe was filled with gas, and before that, plasma. And you could definitely send sound waves through that stuff. In fact, it'd be a much easier place for sound to propagate than it is today.
Do you think it was so, and not to, a Big Bang, I know it wasn't like a bang, but was there a massive amount of sound? Was it like an explosion?
Well, there was a ton of energy in a very small amount of space. So, I mean, it would be really hard to measure that sound in the first seconds or something. But yeah, it would have been really loud in that sense. What I can say is that when we measure the light from the cosmic microwave background, this light that was released into the universe a few 100,000 years after the Big Bang, we can actually see the evidence of the sound waves imprinted on it. We call these the baryon acoustic peaks, but basically they're sound waves from the densest parts of the universe were kind of collapsing and then bouncing outward, and that led to kind of bouncing sound waves through the gas that existed at the time. And we measure that in quite some detail. You can plot it in a way, and it looks like a sound wave. These high density regions basically operated like musical instruments.
Wow, that's pretty cool. And I have seen something or heard something where they recorded some kind of sound wave from space, but I can't remember exactly what it was from. It might have been.
I have a guess.
Yeah.
I have a guess that is from the LIGO detections of mergers of black holes.
Yes, I think that's what it was.
So these are not literally sound waves. But when these black holes merge, they create waves made of space and time. So normal, like sound waves are like just atoms moving around in a medium. Here, the thing that's moving around is actually the space and time itself. And those waves travel to us, and our detectors are now capable of observing them just for the first time very recently. And if you just turn those waves at their frequency and amplitude and everything into sound waves, it turns out it's right in the frequency range your ear can hear. They kind of sound like a little chirp.
Wow, that's pretty cool. The sounds of the universe. There you go. Hey, that could be on your next podcast. Why This Universe? The sounds of the universe.
I mean, we have to do that sometime. That's a good one. That's a good idea.
It's interesting, to say the least. Speaking of sounds of the universe, unfortunately, we have to end the show now. And it always flies by when you're on, and definitely have you back on because it's always a blast.
Awesome.
And I want to lead the show out with a song from your band, The Congregation. And I figure Right Now Everything is kind of the best one because it's kind of quantum entanglement to me is Right Now Everything, the superposition. So thanks again, Dan, for coming on the show.
Sure thing, Damien.
And I'll talk to you soon. And this is The Congregation with Right Now Everything.